Welcome to Rossing Connection, a podcast about all things Lehigh engineering. Coming to you from the P.C. Rossing College of Engineering and Applied Science at Lehigh University. It's a show for students, alumni, faculty, and staff, current, former, and future, and for anyone interested in the many creative ways that engineers are solving the world's problems. I'm your host and producer, Christine Fennessy. This past Christmas, the James Webb Space Telescope launched from Kourou, French Guiana. It's the largest and the most powerful space science telescope that has ever been built. And according to NASA, it will transform how we think about the night sky and our place in the cosmos. It'll help us answer questions like, where did we come from? And are we alone? Webb will be able to see everything from the first galaxies to black holes to exoplanets. To do all that, Webb required engineering that pushed the boundaries of ingenuity and innovation. It took 2 decades, thousands of engineers, technicians, and scientists, and millions of hours to build. One of those engineers is Lehigh alum Scott Willoughby. He graduated in 1989 with a degree in electrical engineering. Today, he's the vice president and program manager for the James Webb Space Telescope program at Northrop Grumman. He's been in that role for 12 years and at Northrop Grumman for 32, basically ever since leaving Lehigh, although back then the company was known as TRW. Northrop Grumman is NASA's main industrial partner for the Webb mission. In this episode, Willoughby explains what makes this, as NASA calls it, an Apollo moment for science. What makes this telescope a singular marvel of engineering, and how we're already benefiting from Webb's development here on Earth. Thanks for joining us. If you asked Scott Willoughby if he'd been the type of kid who obsessed about space, you won't get the answer you're probably expecting.
I really didn't. I always was a nerd about things, puzzle solving. I like space. I watch Star Trek.
So when Willoughby came to Lehigh in 1985, he wasn't targeting a career exploring the cosmos.
I really just like solving problems.
After graduating in 1989 with a degree in electrical engineering, he started working for TRW, now called Northrop Grumman. They put him on their space program, and that's what hooked him. He says working in space seemed almost magical, because it was one thing to create something you could hold in your hands.
But the idea that I was building something that would just leave and go thousands of miles away from Earth and have to do its job, wasn't going to return, no ability to service it, it puts a lot of pressure on you. And for some reason, I enjoyed responding to that pressure. So it felt like it was a harder job.
Now, to the layperson, part of the magic of space might be this idea that telescopes like Webb are often referred to as time machines.
The reason it's a time machine, and one of the easier references is our own sun is about 93 million miles away from us. And we look at it and we see the light. Even at the speed of light, that light that left the sun took 8 minutes to get to our eyeballs because it still had to travel a distance, 93 million miles. So in effect, we are looking at the sun as it was 8 minutes ago. So imagine this. Imagine I collect light from some object that was so far away from me that that light took 13.5 billion years to travel to our telescope. And literally that's what we're doing. And when that light left that star, that's long since gone. You know, that star doesn't even exist anymore. It lasted 4 or 5 billion years. But 13.5 billion years ago, when this star formed, the light started emitting from it. It's so far away from it that it's just reaching us now. And our telescope catches it. And when it catches the fingerprint of what it looked like when it left.
He says this idea that photons are traveling forever in this infinite expanse of the universe and carrying the fingerprint of stars that don't exist anymore can be hard to wrap your head around. But he's had a lot of practice explaining it to a lot of different audiences.
Actually, one of the most intimidating talks was to my daughter's 5th grade science class, right? You know, and then on the other end of the spectrum, I'm talking to professors at world-renowned universities. We want to see how the first stars formed because they actually were the stars that created our periodic table.
He says the Big Bang generated subatomic particles that eventually formed the first two elements of the periodic table, hydrogen and helium.
And what a star is a fusion reactor that burns that hydrogen as fuel. But when it burns it, fusion means it adds it together. Hydrogen and helium fuse together, they create carbon and oxygen and all the way up to iron in these initial stars. And when the stars explode, they create gold and platinum and these higher things.
He says those chemicals eventually became us. If those reactions didn't happen, we wouldn't be here. So capturing light from those long-dead stars can help us better understand how we came to be. But until Webb, we didn't have anything powerful enough to see that early light.
Hubble could only look back so far because the mirror is smaller. It only integrates so much information. And because it's warmer, it doesn't see as much infrared. So Webb is big and it's cold. And with that, we see back further in time. So we'll see first stars.
As a quick refresher, infrared light is light we can't see, but we can detect it as heat. And when it comes to space, infrared light holds a lot of clues. As Willoughby says, it carries the fingerprint of the first stars, which helps us understand the early universe. Infrared light can also penetrate clouds of dust and gas, which unveils the objects that gave off that light. Infrared can also reveal bodies of matter that are too cool or too faint to be detected in visible light, like young planets. Webb has a mirror that can capture all this infrared and turn it into images. But in order to do that, it has to be really big and very, very cold.
So we have to be colder than what we're looking for. So one of the things that makes Webb unique from Hubble is we're running our optics. We're going to operate on orbit at minus 400 degrees Fahrenheit. These are what we call cryogenic temperatures. Only 38 in the Kelvin scale, meaning only 38 above absolute zero. So that's an engineering marvel to design something that has to survive temperature at minus 400 degrees Fahrenheit. The coldest on Earth has been like minus 125 somewhere in Siberia. That's the coldest humankind would have ever been able naturally to experience. So we're going to be operating at minus 400. And we're also going to do that with an optic 7 times bigger than Hubble. So if you take those two things, we're 7 times bigger than Hubble, and we're operating at minus 400 degrees. With that, we're going to catch photons that are 13.5 billion years old.
If you're still having a hard time wrapping your head around just how powerful Webb is, consider this fun fact. It's from NASA. Webb is so sensitive, it could theoretically detect the heat signature of a bumblebee at the distance of the moon. But why do we care about catching 13.5 billion-year-old photons? Why does this mission, which took 20 years, 40 million hours of work, and nearly $10 billion, why does it matter?
Following our curiosity is important. And when you do that, often other great things happen, right? You advance technology for your purpose, and it enables you to reuse that for other purposes. But what is our purpose? We're answering questions that are as simple as where did we come from and are we alone? I spoke a little about the where did we come from. We want to know how did these elements in the periodic table form? And when we learn that, it may give us an understanding of how our own planet and star are evolving.
Willoughby says Webb could also help answer one of the most exciting questions there is. Are we alone?
Webb will also train our eye on planets that are closer to us, only like millions of whatever light years away. And it'll look at those planets to see if they have an atmosphere around them that actually could be Earth-like, meaning it may support life like ours. So our eye will be sensitive enough to find as light transits possibly through an atmosphere of another planet, we'll catch that photon. And if it went through an atmosphere, the atmosphere will cause impacts on that light. Like it'll have dips where there would have been, say, oxygen or methane or carbon dioxide. And by reverse engineering that, I can say, oh my gosh, that photon went through an atmosphere. And does that atmosphere look Earth-like? And we are the next greatest mission that is going to help us understand that.
In case you haven't seen it yet, Webb has a pretty iconic look. And when Willoughby describes the telescope, he sounds like a very proud parent.
Webb is actually beautiful. It looks like a work of art. And I'm not saying other people's spacecraft aren't beautiful, but they tend to look like cans and tubes that have optics in them, to shroud the stray light from it or to perform certain missions. Webb isn't. Its optic is so big we couldn't put it in a can. So it's this beautiful set of 18 hexagonal segments that are coated in a thin layer of gold because gold reflects infrared. So we have this giant mirror that's 22 feet in diameter. Huge, bigger than the top of the rocket, meaning it had to be folded, so it's segmented. So you have this massive gold optic that just catches your eye. And then in order to create that thermal condition, I said, to get down to minus 400, we do always have to block the close IR light, which is our own planet, our moon, and our sun. So to block that, we basically deploy a giant parasol, a sun shield, but it's a big umbrella. And that's the size of a tennis court, and it looks like a diamond-shaped pattern.
Here's another NASA fact. That big diamond-shaped umbrella provides Webb's observatory an equivalent SPF of 1 million.
And that's coated in silver and aluminum to help us with the thermal properties. So when you look at Webb, you almost thought the engineers, were artists.
It was a work of art that required the highest order of problem solving.
The number one challenge was that we had to build a telescope bigger than could fit on the top of the rocket. To get out of Earth's atmosphere safely, you have to be protected in a shroud. It's called a payload fairing on the rocket. And that fairing for decades is 5 meters in diameter. Our optic is 6.5 meters in diameter. We've never, ever had to do this in space. We've never had to take a mirror and say, oh my gosh, it's bigger. So we have to actually build it so it's in segments that can be folded back and then subsequently deployed on orbit. And oh, by the way, that giant diamond-shaped sun shield I told you about, it had to be folded like a parachute. So we had to build something that we couldn't send up in the condition in which it was going to operate.
Willoughby says that every spacecraft has its deployables, like the solar array and the communications antenna, but everything else is usually ready to go. Webb is unlike any spacecraft ever built.
Never in the history of humankind has an invention had to go into space and have to get built up effectively as it traveled. So after we launched, I got to go up in the control center for 2 straight weeks. Every day we were deploying something else that was stowed for launch. It was amazing how flawless that went, but it took us 20 years to make that work.
He says that's because the hardest part isn't actually surviving space.
It's testing it on the ground to make sure you didn't fool yourself into thinking it was going to work in space.
Because if it doesn't work up there, there's no fixing it. About a month after launch, Webb reached its final destination, the second Sun-Earth Lagrange point, or L2. It's 1 million miles away, 4 times further away than the moon. Hubble, by comparison, is 340 miles above Earth, roughly the distance between Los Angeles and San Francisco. So if something goes wrong with it, which it has, astronauts can fix it. So Webb's engineers not only had to account for Webb's size and the extreme operating environment, but for its remoteness too. It all required truly next-level creativity and innovation.
It's an oversimplified example of something we've done, but it kind of expresses the ingenuity of trying to trick or defeat gravity on the ground. So the sun shield is made from these, we call them membranes. It's almost like a kid's mylar balloon or the materials that are blocking the sun. And they're very thin. They're 1,000th of an inch thin, but they're 70 feet long by 40 feet wide, right?
Once these 5 giant membranes unfolded in space, Willoughby says they had to assume an almost perfect 3-dimensional shape.
Well, I need to know in orbit how that's going to work in gravity, of course. So if I measure it on the ground, gravity is sagging that thing. And I look at the shape of that. I measure the contour. Well, then what the engineers do is then you turn the entire thing over 180 degrees, and then you lay it face down. And it sags Okay, but it sags in the opposite direction, and you measure with a great degree of accuracy that surface. And then in the computer model, you subtract those two. And the middle state is 0G.
Building Webb's giant gold-coated mirror was another major challenge. The bigger the mirror on a telescope, the more light it can collect, and the more detail it can see. Willoughby's team had to figure out how to build a very big mirror that was light, very strong, and could fold to fit inside the rocket. They designed a mirror made of 18 hexagonal-shaped segments. Each of those segments can be individually aligned so it operates as one single mirror. That alignment takes 3 months, and as of this recording, it's going on right now. Eventually, all those segments will be aligned to within 1/10,000th of a human hair. Willoughby's team also had to account for the fact that materials shrink as they get cold. And to do that, they had to build the mirror, as NASA puts it, precisely wrong.
So while we pick the material, in our case, our mirrors are made out of beryllium, just happens to be a metal that at cryogenic temperatures is really stable, but at minus 400, its surface is going to be a certain shape. But at room temperature, where I'm polishing the mirror, I'm not going into a chamber in a suit at minus 400 degrees, right, and trying to polish this mirror. We're doing it at 70 degrees Fahrenheit. And what the engineers had to learn was, how does that material behave differently at 70, right, versus minus 400? And what we did is we took the raw mirror before it was perfectly machined and we put it in a chamber. We measured how the mirror changed as it went down to its operational temperature. And then we back calculated what would it look like deformed in order to get that precise surface at 70. We polished it blurry. And then we put it back in the chamber and tested it again and brought it down to minus 388, minus 400, and proved that it set itself. And then what was the perfect, call it parabolic shape. So again, you had to basically polish blurry so that when it changes, almost 500 degrees in the Fahrenheit scale, it crisps up into the pattern that you want.
When Webb launched on Christmas Day, it was folded up like a giant piece of origami inside the Ariane 5 launch vehicle. About 30 minutes after launch, it started to unfold, and that process continued nearly every day for 2 weeks. It was an incredibly stressful time for everyone on the team, in part because a successful deployment meant overcoming nearly 300 single points of failure, meaning if a part fails, there's no redundancy for it.
There's never been something built that had that many single point failures. Even some of the very complex things we've done, like landing on Mars with the Perseverance, rover, and before that Curiosity, they had less than 100.
By January 8th, Webb was fully deployed after a process that Willoughby calls flawless.
The team just nailed it. And there was almost this comment, well, if it went so perfect, was it ever really as hard as you said it was going to be? It's like, yes. What we did was, it was hard on the ground. The tests we did on the ground had to confess every weakness to us. Even weaknesses that probably would have never been an issue on orbit. If we saw those, we corrected those also.
Willoughby had a team of engineers whose entire job didn't involve how to make things work. Instead, they figured out what to do when things went wrong.
We had an entire plan that if our solar array didn't deploy, if something stuck, what if I then change the sun angle and make it either expand or contract? Maybe that'll release it. What if I fire my thrusters and shake it a little? Would that nudge it past the point where it was? Turned out I didn't need any of those. But I had a team that spent years coming up with contingency operations for that one thing. Because if it didn't work and you don't have a solar array, then your mission doesn't continue, right? You're not getting electricity from the sun. So my fault management team went through everything, and it helped the designers say, wow, if that's really can go wrong, well, first of all, can I prevent it? But oh, by the way, I never accepted that, don't worry, we designed it out. I still wanted to know, your job is assume it went wrong. I don't care what the engineer tells you that it can never happen. You assume it goes wrong, tell me what you would do today. And you needed to have that written down in a procedure such that we didn't think about it the day it went wrong. We were ready to enact it as soon as it went wrong. So there's engineers who just do that.
Willoughby got into engineering because he liked solving problems. And Webb is a masterpiece of problem solving. Building it required so much imagination and ingenuity that it spawned new inventions and technological breakthroughs that are being used today in industries pretty far removed from space. One of those developments is a direct result of work that was done on Webb's mirrors.
Those mirrors have a surface figure accuracy, meaning how well they represent the concave shape we intended them to be. That is so perfect, it's measured in what's called nanometers. So each of our mirror segments is as accurate to better than 20 nanometers. But how do you test something that is so fine? How do I prove that the surface of this mirror really is that good? And we use actually the speed of light to our advantage. It's very well known, and we use laser interferometry. What it means is I bounce light off of a spot on the mirror, and I know how far away I am from the mirror. I hit it with the light, and the light comes back. And depending on how long it took for the light to return, I know how far it traveled. So if there was a little dip in that mirror, it would have to travel just a little bit further, right? And then it'd come back to me. Well, NASA and Northrop came up with such a precise technique to do these mirrors that ophthalmologists now use that to measure your eyes. So when you go in for LASIK and for other things to characterize the shape of your eye, which is very important to understand the curvature and how that works, that technology that we used to measure our mirrors a decade ago right now is being used in ophthalmology to perfect how great of a prescription they can give you, how well they can measure your eyes.
He says that's just one of the inventions inspired by Webb. And there's another one that blows his mind. This one is a spin-off from the Hubble Space Telescope, and it's a lifesaver.
You know, when Hubble launched initially, it actually had a blurry optic, and it got famous and infamous for that, but then it was corrected. But before the astronauts corrected Hubble, the scientists were like, well, at least I got blurry images. I want to find something in there. And they created these computer models to try and find what was the real data inside the blurry data. That's used in mammograms right now because that's how you find cancerous tissue and good tissue. So this failure leading to inspiration to solve a problem, to come up with a technique, is now how we try and find something within our bodies. There are just so many stories like that that are wonderful.
That's almost it for today's show. Webb is still in its 6-month-long process of fully deploying, cooling down to its operating temperatures, aligning its mirrors, and calibrating its instruments. So it's not going to start collecting any images until about June. But you can keep up with its progress. Just search, "Where is Webb?" I'd like to thank Scott for being so generous with his time. It's such a busy and historic moment. For more information about all the academic programs at the P.C. Rawson College of Engineering and Applied Science, and to find our show, head to engineering.lehigh.edu. Music in this episode is by Blue Dot Sessions. You can subscribe to Rawson Connection wherever you get your shows, and send us story suggestions or feedback on Twitter @Rawson Podcast. Thanks for listening.